Welcome to the second lecture on stack-based programming using PostScript as our example language. So the outline for today, first we'll have a quick introduction to the basic concepts of the PostScript language, including objects, types, and stacks. We'll look at arithmetic operators, graphics operators, we'll see how we can define our own procedures and manage variables, and finally at the end we'll see how, with the help of the dictionary stack, we can create higher level abstractions. The material that I'm using is rather old, dating from the 1980s, which is when the PostScript language was introduced. These books are available as PDFs from the course website. So, first of all, what is PostScript? So PostScript is described as a simple interpretive programming language to describe the appearance of text, graphical shapes, and sampled images on printed or displayed pages. In actual fact, PostScript has become, since the 1980s, the de facto standard for pretty much all printers. So when you print something on a printer, what actually happens is that a PostScript program is generated and sent to the printer where it's interpreted to produce the printed pages. It was introduced by Adobe in 1985, and it is pretty much the de facto standard. The language itself is pretty interesting. So it's a stack-based programming language. As we'll see, everything is done with the help of stacks. So it's, on the one hand, a fairly low-level language, but it has everything that you need to build higher-level abstractions. The syntax is really minimal. We'll see it in just a couple of slides. It has a large number of built-in operators to perform not only calculations, but also everything that you need in order to construct graphics on a printed page. Usually, people don't write PostScript programs by hand, but in fact, they're generated from applications. The language has gone through several evolutions. The original language, the level 1 version of the language, was proposed in 1985. Then additional support for dictionaries and memory management came. Interestingly, in the late 1980s, display PostScript was introduced. There the idea was, instead of using PostScript only to produce printed paper from printers, that it could actually be used to provide support for the display on the screen. One of the machines that supported this was the Next machine, which was a project of Steve Jobs after he left Apple in the 1980s. The Next machine had support for display PostScript. Many years later, when Steve Jobs came back to Apple, he brought the operating system, the Next operating system, with him to Apple, and it formed the core of the support for the new operating system for the Macintosh. Interestingly, the display PostScript, even though it wasn't used for the windowing system, stayed in the system so that even today, when you have a PostScript file on a Mac, you can just double-click on the file and it will get immediately interpreted. Nowadays, instead of directly displaying on the screen, however, a PDF file is generated and opened, as we'll see. The syntax of the language is extremely simple. These are the basics of it here on a single slide. So we have comments starting with a %sign. We have support for a variety of different kinds of numbers. Strings, of course, we need to print strings, so there has to be support for strings as a basic data type. They're text within parentheses, or sometimes in hexadecimal with angle brackets. Special characters have to be escaped with a backslash. Obviously, parentheses themselves as characters have to be escaped. Names are tokens consisting of regular characters but aren't numbers. Literal names start with a slash. And this is important, as we'll see, when we want to define variables or define new procedures. Then before they exist, we'll have to define them by introducing a literal name. Afterwards, we can use them through the regular names, once they've been defined and introduced. Arrays are within square brackets, and finally procedures are in curly brackets. A PostScript program consists of a sequence of tokens. They represent typed objects, that is, different kinds of entities, as we saw, procedures and strings and numbers and so on. And this sequence of tokens is then interpreted to manipulate the display. It's a stack-based programming language. There are in fact not just one stack, but 4 different stacks, and we'll essentially see 3 of them. One is the operand stack. The operand stack is where we push operands for operators, so they're pushed onto the stack, and when we execute an operation, that operation will pop values off the stack, produce the result, and push any results back onto the stack. Later on in the lecture, we'll see there's also a dictionary stack. The dictionary stack allows us to have a whole sequence of different scopes. Every dictionary defines a scope with a collection of keys that are bound to values, and the visibility is from the top down of the stack. So when you're looking up a name that's been defined, you're going to be looking in the dictionary stack from top to bottom. When you push a new dictionary on, then the names in that dictionary take priority over any that are below. When you pop a dictionary off, all of the names defined in that scope disappear. We'll get to that at the very end of the lecture, where we'll see how that's extremely useful to define higher level abstractions. The execution stack we won't see explicitly. That's what PostScript used internally to manage the stages of execution of procedures. Finally, there's a graphic state stack, and this allows us to keep track of the current coordinates of something that we're drawing. As we'll see, this is also extremely useful because this allows us to draw things in a very simple coordinate system, and we simply can scale and rotate and translate the coordinate system itself rather than the objects that we're going to draw. We'll see a very nice example of that at the very end of today's lecture. The types of objects, every object is either literal or executable. So a literal object is one that's going to be pushed onto the operand stack. So when we have a program consisting of a sequence of tokens, if we see a literal object, all we do is we push it onto the stack. If, on the other hand, we see an executable object in our program, then we, instead of pushing it onto the stack, we'll execute it. These include both built-in operators and names that are bound to procedures, so ones that we define ourselves. Then there are simple object types. They're copied by value, so booleans and integers and names and so on. They're pushed directly onto the stack or copied by value. And composite object types, like arrays, dictionaries, and strings, they're copied by reference. But that's completely transparent to us. So when we push an array, we have the impression that the actual array is going onto the stack. Whereas in the implementation, it's essentially only a reference to a pointer to that array. Next, let's have a look at arithmetic operators, and we get a bit of a taste of what PostScript looks like and how it executes. So here's our first tiny little program in PostScript. So the program consists of the text 40, 60, add 2 div. 40, 60, and 2 are literal objects, they're numbers, and add and div are executable objects. Those are built-in operators in the language. What we see rendered here on the left is a visual depiction of the stack, the operand stack. When we execute this program, stuff will get pushed onto the stack, stuff will get executed, and in the end we'll have the result on the top of the operand stack. What is this going to do? Well, this is going to push 40 and 60 onto the stack, add them together, push 2 on the stack, and then divide. In other words, we're going to compute the average of 40 and 60. So, first we see 40, it's a literal object, we push it on the stack. We see 60, it's a literal object, we push it on the stack. We see add, add's an executable, so we run it. Add is going to take the top 2 things on the stack, pop them off, add them together, take the result, and push that on the stack. So 60 and 40 are consumed, 100 is produced and pushed onto the stack. Next we see 2, we push that onto the stack, and now we execute div, which pops 102, divides the 100 by the 2, and pushes the result back onto the stack. Note that the computation here is expressed in what's known as reverse Polish notation. This means that operators always appear after their arguments. This is a very interesting syntax for languages, and it was popular in certain kinds of calculators, particularly those coming from Hewlett-Packard. Why? Well, as you may have noticed, we don't need to do anything special in executing this this stack-based language. We don't need to parse the program. We just execute everything that we see as it comes along. If it's literal, we push it. If it's executable, we execute it. We don't need to parse anything or interpret the structure of the program. So this means that when you implement such a stack-based language in reverse Polish notation, the implementation is really trivial. So that means that you can build your machine very cheaply. So in the case of Hewlett-Packard calculators, by forcing the users of the calculator to express their calculations in reverse Polish notation, they save themselves money by not having to build any kind of clever parsers into the calculator itself. They simply execute every command as the keys are pressed on the calculator. So here are some of the basic stack and arithmetic operators. Obviously, it's not all of them. Notice the style in which we express them. So in the column labeled stack, those are the operands, the arguments that we expect to see on the stack. Then we find the operator, and then we find the result. So the type of the add function, or operator as you will, is it maps from two nums onto a sum. And all of these are expressed the same way. Add consumes two things and produces one thing. Sub or subtract does the same. Also multiplication and division, they all take two arguments and produce one result. Then we have integer divide, modulo. There's a whole bunch of trigonometric operators like arctangent, sine, cosine, you can imagine them all. There's a special operator pop that just gets rid of the top thing on the stack. Notice that there's no operator called push. Why? Think about it for a moment. We don't need it. Push is the default operation that's performed whenever we see a literal object in the program. So in order to push an element x, we simply name x, the literal value x, in our program. Then there are a bunch of other handy operators for manipulating the stack. Exchange will swap the top two elements. Dupe will duplicate the top element. We'll be needing that later on. Copy is an extension of dupe, which will copy the top n elements. And index will reach down into the stack and pull something that's deeper down in the stack and copy it to the top. Okay, now let's start having a look at the graphical operators. PostScript assumes that we have a drawing space which represents a piece of paper. For example, a piece of A4 paper. One thing that's useful to know that is in typesetting, coordinates are measured not in inches or centimeters, but in so-called points. So when I have 12-point type or 10-point type, these points refer to a specific measure. In particular, 72 points is exactly 1 inch or 2.54 centimeters. A sheet of A4 paper is 595 points wide and 840 points high. The coordinate system that PostScript uses assumes that 0, 0 is at the bottom left. So those are our XY coordinates. Here's our first PostScript program that we can actually execute to print something. And here we're going to draw a box. in order to draw a box, we have to first create a path. So the idea is that you define a path. So here, the first operator we use is called new path, so it clears the current drawing path, and a path is going to consist of a number of points on the sheet of paper. So first we'll move to the position 100, 100, that is 100 points to the left and above the bottom left corner of our sheet of paper. Then from that point we will draw on our path a line to position 100, 200, then up to 200, 200, back to 200, 100, and all the way back down to 100, 100. All we've done so far is defined a path. We haven't actually drawn anything on the paper. Next, we can set the line width to draw. So here we set it for 10 points. Still, we haven't done anything. Now we execute stroke. So what stroke does is it takes the current drawing thing at the line width of 10, and it follows the path and draws. So now we have drawn something on our sheet of paper, but we haven't printed it yet. Finally, if we say show page, that means we're done with the sheet of paper, we send it off to the printer, and it gets printed. So you can actually take this program and send it to your favorite PostScript printer, and it should produce a piece of paper with this thing drawn on it. Let's have a look at what that looks like. So, in the repository of examples for this course, you will find a folder called PostScript with a number of examples in it. These are all the examples from this lecture. You will find the first box.ps file, and this is its contents. If we execute that with a PostScript interpreter, or in the case of the Macintosh, we simply double-click on the file to execute it, we will then see the results as follows. When we execute this program, by running it through our favorite PostScript interpreter, or in the case of the Macintosh, simply executing the file by double-clicking on it, we get the following output. As we can see here, we started it in position 100, 100 from the bottom left corner. The path was drawn to the right, up, left, and down again. Then we stroke, that is, we drew along this path, and finally we produce this output. In this particular case, on the current Macintosh, what is produced is a PDF file that we've actually opened in the preview. Now you may notice that in the bottom left corner, something isn't quite right. Think for a moment why that is so. You can stop the podcast for a moment and consider it, and then when you think you have a solution, please start again. Okay, so what's actually happening? This result is correct. What we've done is we started with our drawing pen at a width of 10. We moved to the right. We turned, moved up, turned, moved to the left, turned, and moved down. And the problem is that at the end, our results, our pen results, didn't match up. So they're actually aligned right at the center there. In order to fix this problem, this artifact, we actually have to close the path. So there's another operator in PostScript that helps us do that. Continuing on, here are the various operators available in PostScript to construct paths. So first is new path. It requires no arguments. It just initializes the current path to be empty. It doesn't do anything with the stack. Current point tells us where we are and pushes x and y, the current coordinates, onto the stack. If we have two coordinates, x and y, we can move to that location, or what's more useful sometimes is to move a relative distance. So instead of x and y, we can say delta x and delta y. We can also append a straight line to the path, and there's also a relative version. You can also draw an arc, which can be a complete circle or a partial arc of a circle. Here's the operator we were missing, which was close path. We'll be using it later. So this makes sure that when we're at the end, we complete the path and we don't have any funny artifacts where the end of the line meets the beginning. End of the path meets the beginning. Fill is used to fill whatever shape that we've created with a grayscale or with a color. Stroke, as we've seen, draws the line across the current path. And finally, show page terminates our current page and releases it to produce a PDF file, or in the case of a printer, to actually print the page. Now we can do Hello World, which is a little bit more complicated than it is in many other languages. So to actually print Hello World on a piece of paper, we have to do some additional work. We need to pick a font, a typeface, look it up, scale it to the right size, set it to be the current font, then figure out where on the page we want to print it, print that text, and then show it, and then finally produce the output page. So here we can see that. We take the literal string times Robin, push that onto the stack. We say to PostScript, please find that font and leave the font on the stack. Then we have to scale that font. So in this case, we want it to be 18 points high, be nice and visible. Then we set that to be the current font using the set font operator. Now we move to position 100, 500, move to that location. We push the string Hello World onto the stack and execute show. Show will then produce that text on the page at the location that we are currently, and finally we render the current page. Let's have a look at what that looks like in practice. So by executing the Hello World program, here's the result of executing that program. As you can see, we are 100 points to the right of the bottom left corner and 500 points up, and the text Hello World is rendered at 18 points size. Now there's a dialect of PostScript called encapsulated PostScript, not really a dialect, it's just a commenting convention. If at the first two lines of your PostScript program you include the following commented lines, then you can encapsulate your PostScript output. So in this particular case, the first line says that we're PostScript Adobe 3.0 and we're using encapsulated PostScript 3.0. The next line is important and it defines a bounding box. And here we put the bounding box to just below 10 points below and to the left of our Hello World, and finishing at 200 points to the right and 520, another 20 points above the bottom of our Hello World. So this will put a bounding box around that text, and any program that wants to import our encapsulated PostScript will ignore everything outside of that bounding box. So I could actually use this to take the PostScript programs that we had and import it directly into certain word processing systems or even slideware. So without having to generate an image from the result of the program, I could take the program and directly import it into my application. So there are a bunch of dedicated operators in PostScript for managing fonts. We've already seen find font, scale font, and set font. We can also ask what the current font is. We've seen how to print a string at a particular location. We can also ask what the width of the string is in the current font, and this will be helpful to us later in a couple of further examples. Next, let's look at how procedures and variables are defined in PostScript. Variables and procedures are handled in the same way. We simply define them by binding a name to either a literal or an executable object. It works with the operator def. It expects to find on the stack a key and a value. The key has to be a literal name, but the value can either be a literal value or it could be a procedure. So here in this example, we're going to define a procedure to compute the average. It works as follows. We first push the literal name average onto the stack. Then we write the procedure, curly brace add to div, and that pushes that procedure onto the stack. Note, of course, in the implementation that procedure is not literally on the stack, but only a reference to it is. But for all intents and purposes, it's the same. Now we execute def, which takes those two values from the stack and binds the name average to the procedure. Now, if we execute 40, 60, and average, what will happen is 40 and 60 get pushed onto the stack, and then average is executed as if it were macro expanded. That is, we perform add, we perform 2, pushing 2 onto the stack, and we execute div, which leaves the average of the two values on the stack. Now, something a little bit more challenging. We would like to have a general procedure for drawing boxes. Now, in this program, which is just a little bit more complicated, we can see how a PostScript program is usually divided into two parts. There is a prologue, which defines all sorts of useful procedures, and a script. In fact, in most applications that print that produce output for printers, they work in more or less the same way. So if you have your favorite word processing program where you can write a text, a letter, a document, when it produces, when you ask that document to be printed, what will happen is that there is a whole prologue of pre-existing, predefined procedures and variables and so on, which are spit out. They're the same, so it's essentially the library. And then from your document, a script is generated, and that script will call the library functions in the prologue in order to actually print your document. So this is a baby version of what will happen when you print something from your average application. So here we've defined a box procedure. So we write /box. It's a literal at this point, and we want to define what that literal stands for. As a comment, we see that box is expecting three things on the stack: a gray value and an X and a Y. And it leaves nothing on the stack. How is it implemented? Well, first we have to clear the path, so we say new path. Then we move to the position XY. Then we execute relative line twos to draw a path of a box of 150 times 150 points. We close the path cleanly. Now we consume the gray value, which is still left on the stack, by calling setGray. Now we've consumed all the values on the stack, all of our three operands, and we finally execute fill. So that will now fill in the region. So that's now defined as the box procedure. Now we have our script. We say 0, 100, 100 box. That will put a black box at position 100 and 100. Then we have 0.4, 200, 200. That will draw a new box slightly to the right and above with a grayscale of 0.4. And finally, we have a lighter box, again to the right and above, with a grayscale of 0.6. Finally, we set the grayscale back to 0 so that we continue drawing anything in the future back in black. To manipulate the graphics state, we've got a number of operators, some of which we've seen. So we can set the line width, we saw that much earlier. We can set the grayscale. We can scale the user space by SX and SY. So when we scale, we don't need to scale the same amount in both directions. We can also rotate the user space by a certain angle. We can translate it by TX and TY. And all of these operations that are manipulating and translating our coordinate space, our user space, they can be stored in a so-called matrix. This matrix is what's responsible for doing the translations. So we can create an identity matrix with matrix. We can fill that matrix with the current matrix. We can replace the current matrix by a given matrix. We can save the graphic state, and we can restore it. Why do we need all these things? Well, imagine that you wanted to draw a box which is rotated and translated. In order to figure out exactly what needs to be done to achieve that, it would be very painful. What you can do instead is you can assign that box to a particular user space, and instead of rotating the box, you rotate the entire space. That makes it trivial to draw the box as though the page were untranslated, and then translating the whole user space will translate all of the objects in the way that you like. Translate, rotate, scale all together. This transformation that's performed can be saved, so it's applied to everything that it needs to be applied to, but you can also save and restore the previous space so that once you've done performing these operations, you can go back and leave the PostScript executing system in a clean state again. We'll be using that shortly in order to draw arrows which are pointing in a variety of different directions, and that'll make our job much, much easier. But before we get to that, let's see a couple of other examples. Here's an example of a Fibonacci graph. So what we're doing is we're graphing the Fibonacci values, scaling it, however, because Fibonacci grows way too fast. So in order to draw this graph, we need a bunch of things. So first of all, we need to compute the Fibonacci values. As we all know, Fibonacci is, if it's implemented naively, highly exponential, but if you implement it in a clever way, then it can be computed linearly. So the trick is to always compute two Fibonacci values together, and then the recursive algorithm ends up being linear. So fib_inc assumes that on the stack are the last two Fibonacci values, and what it will do is we'll increment those, so it will bump both Fibonacci values up by 1. So if m and n are on the stack, we expect to find, after running fib_inc, n and m plus n on the stack. This is quite straightforward to do. First, we perform an exchange. So instead of m and n, now we have n and m. Then we use index to copy the value n up to the top of the stack. And then finally we add. So with these three operations, we performed an increment, and we've updated the top two Fibonacci values on the stack. Now we define as variables a bunch of values. We define x and y as 0 and delta x as 10. We create a new path. Instead of moving to position 100, 100, we translate our user space to position 100, 100. So our 0, 0 location is actually on the sheet of paper at position 100, 100. But for the purposes of drawing our graph, it's much more convenient to think of that as 0, 0. Now we initialize our Fibonacci numbers by pushing 0 and 1 on the stack. Now we use a built-in control operator called repeat. And repeat will execute a procedure a certain number of times. In this case, we want to run 25 times the code that's in between the curly braces. First, we look up x. So first we push the literal value x onto the stack. Then we look up the value of x. Notice the difference between /x and x. /x leaves the literal name x on the stack. X looks up its current value. dx looks up the value of delta x. Now we add the two and we run def, which has the value of updating the value of x to the new incremented value. Now we want to set y to be 1/100th of the last Fibonacci value. Notice we're incrementing x, but we want to compress the y-axis, so we're actually going to divide the y values by 100. We could have achieved the same instead by scaling our user space, but we didn't do that here. So that's an exercise to the reader. Instead of incrementing x by 10 and dividing y by 100, have the same program where x and y are just where x is incremented only by 1 and the y-axis is scaled using the scaling operator. Now we draw our segment to the new position of x and y. We increment our Fibonacci values and we repeat 25 times. Finally, we set the line width to 2 and we actually draw and produce the page, and that produces the output that we see here. Strings can be directly printed on the screen, but numbers cannot. So in fact, in order to produce a certain number and print it, it needs to be converted into a string. The string operator will take an integer and create a string of that capacity. So it's a memory management function. CVS will take any string and convert it to a string, as we'll see. The next example is going to use these operators. We'll write a program which is going to display the values of the of factorials. So we'll need a factorial procedure, but we'll also need to do a little bit of extra work because the output that we want to see is going to look like this. So we'll want to say that 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and so on, as we see on the right. Now let's see how the program actually works, because there's a fair bit of work that we have to do to produce this nice output. First of all, we need to define a left margin. So we want to indent from the left-hand border of the sheet of paper. We also want to set the font size, so it's good to store that. Instead of using magic numbers, we'll store that as a variable. We'll also need a buffer of a certain length size in order to store the factorial values. So we're just going to pick the value 20 as being long enough. So we create a string buffer, which is a string of length 20, and we define the literal sbuff to be bound to that. Now we define a factorial procedure, so we push the literal value fact onto the stack and the procedure, and we bind it. What does the procedure do? Well, factorial should take an n from the stack and leave n factorial on the stack. So the first thing we do is we duplicate that n, and we ask if it's less than 1. So this leaves n and this boolean on the stack. And now we see two procedures and an if-else. What the if-else will do is we'll look at the boolean on the stack and we'll execute either the one procedure or the other. So if the value on the stack, if the number n is less than 1, then we'll pop that value and push 1 onto the stack. So because the factorial value that we want to return is 1. If, on the other hand, that number is not less than 1, what we're going to do is the part that's shown in the second procedure. First, we duplicate n, we push 1 on the stack, and then subtract it, so that leaves n and n minus 1 on the stack. And now we recursively execute factorial. Executing factorial will leave n minus 1 factorial on the stack, and now all we have to do is multiply them. So the last step is multiplication, and that leaves n factorial on the stack, as expected. Now, that's just the computation. We still have to manage all the printing. So here's a little procedure which will convert an integer to a string, because we can't print numbers, we can only print strings. So what showInt will do is we'll take a number n from the stack and consume that and show it at the current location. So in order to do this, we take our buffer, sbuff, and we run convert string. Convert string will take the string representation of the number that's on the stack and leave it in sbuff. So now the number and sbuff are consumed. And finally, we run show. So and the string is left on the stack. And finally, we show that, and it disappears too. So summing up again, showInt expects n on the stack. It will consume that, leaving a string representation of that number on the stack, and show will consume that and show it onto the piece of paper. We still have to do a little bit more work. Now showFact will take a number n on the stack. It will show it. It will also show factorial equals, and finally it will consume, compute the factorial of that number and show it as well. So that's going to be one line of our output. Now we have to do a bit more work because we want to produce one line for each factorial value from 0 up to 20. So here's yet another procedure, new line. So new line will advance us one line down from where we currently are and move us to the current indentation that is at our left margin. So after printing a line, what new line is going to do, it looks at where we are currently. So the current point is going to be xy. We're going to exchange those and pop off the top value. So this will leave on the stack the current y value. So this is how far we are down on the page, or up on the page, if you will. We're going to subtract from that value the font size plus 2. So we add the font size, which is 18, add 2 to that because we need some space in between the lines. So now we have 20. We subtract that from y, and that tells us where the new y location is. Now we simply move to the new xy. What's x? X is just the left margin, and the y is the one we computed. So what the new line procedure is going to do every time we execute it is going to take our current position, move us back to the beginning of the line, and go down an extra line. Finally, we have our script. We find Times Roman, we scale it and set it as the font. We move to the left margin at 600 points up the page, and then we have a for loop. So it's going to do from 0 up to 20, incrementing by ones. We're going to show each factorial value and do a new line, and finally we show the page. So it's a fair bit of work to do our factorial, but we're not just computing factorials, but also figuring out where on the page to print, and we're computing our line locations. We've seen a whole bunch of new operators. There are lots more, so there are all sorts of Boolean control operators. We can test for equality, not equal, and so on. True and false are operators, but they're essentially can be treated as literal values. So when we execute true, that leaves the true Boolean value on the stack. Same for false. We have an if then else, a for loop, repeat, and so on. And with strings, we can ask the length of a string. We can get an element at a particular position in a string. We can put a particular value at a position in the string. And we have a for all operator as well. If the last example wasn't enough for you, here we have a very simple formatter. Now, in reality, when you have a word processor, all the computation of where the words go and how they're positioned on the page is computed not in PostScript, but in the word processor itself. And all that PostScript is used for is the rendering. But since PostScript is a fully blown programming language, we could actually implement a formatter in PostScript itself. So you have a lot of choice. You can do computation on your computer or actually offload a lot of computation onto the printer itself. That's probably not the most efficient way of executing programs. So here we define a left margin, a right margin, a font size, and a showString operator, which will print a string. What it will do is it'll ask for the width of the string that is going to be printed. So our operand, our argument to this procedure is the string. Where we ask for a string width. So first we duplicate the string. We ask for string width, which gives us both the height and the width, and then execute a pop because we only want the width. Then we find our current X position. Now we add those two numbers, and that will tell us where printing that string would bring us. And if brings us beyond the right margin, then we're going to do a new line. Now we're ready to actually print the string. So that's the showString operator. The new line operator was essentially the one that we saw in the last example. It computes where we are currently, does a carriage return by going down the font size +2, and moves us to the left margin. So it's just like what a typewriter would do when you do a carriage return. We have a format operator, which will now can be used to format a sequence of words. So basically what it's going to do is it's going to run showString on each of the strings in our argument with a blank in between them, and then at the and show each of them. And finally we look up the font, scale it, set it to the font, get into our initial position, and then we can actually have our script. So here's the script. We take an array. Now is the time for all good men to come to the aid of the party. Execute format on that and show page. And this is our result. Now, the last part of this lecture, we will see how we can use the dictionary stack to create higher level abstractions. We've already seen briefly the start and end array construction. With a left square bracket, we can list a number of objects that form the content of the array, and the right square bracket will end the array and leave a reference to the array on the stack. You can create an array of a certain length, ask what the length of the array is, get any value at any position in that array, put values in that array, iterate over the array with for all. We've already seen that. And now we have dictionaries. So dictionary is a set of key value pairs. By saying int dict, we will create a new dictionary of a certain capacity that will hold an integer number of key value pairs. You can ask what the size of the dictionary is. You can also ask what its capacity is. So the length will tell you how many keys and values are currently in it. Max length will tell you what the actual capacity is of the dictionary. By saying dict begin end, dict begin will push that dictionary onto the dictionary stack, and popping it will happens with end. So what effect this has, if you create a dictionary and put keys and values into it, everything that's in that dictionary is available to you, whether it's a variable or a procedure, as long as that dictionary is on the dictionary stack. The moment you say end, you pop that dictionary off, and everything that's stored in that dictionary is no longer in scope. It's no longer visible. Pushing the dictionary back onto the dictionary stack, the same dictionary which you've stored, will again make all of those names visible. Notice you have a stack of dictionaries. So by pushing a dictionary onto the stack, the values, the keys and values that you've defined there may shadow or hide values that have been defined in other dictionaries below on the stack. Now we'll see an example of how to use this. We're going to write a procedure for drawing arrows. And in order to draw these arrows, we'll need a whole bunch of variables. And we'll make use of a dictionary to keep track of these different variables. On the right-hand side in the diagram, we can see there's a whole bunch of variables we need to configure to specify an arrow. So it has a tail, so that's in the middle of the tail, that's a particular location, tail x, tail y. It has a head, a tip x, tip y. The head has a certain thickness and a certain length, or height if you prefer. And there's also a thickness to the main stalk of the arrow. So if you want to create an arrow, you would execute it as follows in the line at the very bottom of the slide. So you would specify tail x, tail y, tip x, tip y, thickness, head thickness, and the head length, and then execute arrow. So you have 7 different variables which have to be passed to the arrow procedure to draw the arrow. Now, in order to keep track of those variables, there are certain other intermediate variables which we're going to compute that we also need to manage. In the end, we're going to create a dictionary that has room for 14 different keys and values. So the first line on our program here says arrowdict 14 dict def. So that will create a new dictionary called arrowdict, which has room for 14 keys and values. In addition, we see in the program there are 7 variables which are arguments to arrow. There's another 6 which are computed internally, and there's a 14th variable which is matrix, mtrx, which is also needed inside the dictionary. So we also allocate space for a matrix there. Now the procedure arrow itself, it's a bit too long for one slide, so we see the beginning here and the next on the next slide. So arrow, what it's going to do is it first pushes arrowdict onto the dictionary stack with arrowdict begin. Then we grab the arguments, the head length, half head length, and so on. We're going to store all of these, and they'll be available symbolically under these names. Now we compute a bunch of other useful things. So the delta x and the delta y. Delta x is the difference between tip x and tail x, and delta y is the difference between tip y and tail y, and so on. We compute the length of the arrow in the obvious way. We compute the angle that the arrow has to be rotated, because notice tail x, tail y is an arbitrary point, and tip x, tip y is also an arbitrary point. So that means this arrow may be pointing in various directions. We compute the base, which is the difference between the arrow length and the head length. And we save the current coordinate system. So this is important because we're going to play games with the coordinate system. Once we've played those games, in order to draw our arrowhead, we want to be able to restore the coordinate system to the way it was before. By playing games with the coordinate system, we make our job of drawing the actual arrowhead much, much simpler. So instead of rotating the arrow, we're going to rotate the coordinate system. Here's the rest. Now we're going to translate to the start of the arrow, and we're going to rotate our coordinates by the angle that we've computed. Now the actual task of drawing is really simple. So we're at position tail x, tail y. We move negative direction of the half the thickness. Then we go up the base. We move arrow length. We move to arrow length 0 and continue on all the way around until we end back at the tail X, tail Y position. Finally, we close the path and we restore the matrix. So our saved matrix then gets restored to what it was before. Notice that this procedure has done nothing except draw the path. We haven't actually shown anything yet. So that gives us considerable freedom in how we actually use the arrow program. So here, for example, we say new path, we draw one arrow and we fill it, we draw another arrow and we set the line width to 3 and draw a stroke, and finally we have a third arrow which is filled with a grayscale value. So here we see the 3 different arrows, all of them pointing in different directions, but drawn in a straightforward way. As a concluding remark, here we've seen that the dictionary stack is very powerful. So every time we draw an arrow, we push this arrow dictionary onto the dictionary stack. All of these variable names that we've seen are temporarily available, but when we're finished with the arrow procedure, the dictionary is popped and our namespace is no longer polluted with all of these variables. This might sound familiar. In fact, dictionaries can be used to implement an object-oriented system. This is exactly what the language Python does. At the core of Python, everything is a dictionary, and Python builds the whole object-oriented system out of these dictionaries. This is very powerful, and other languages essentially do the same thing. Now, what shouldn't surprise you very much is that in the past, people have actually built fully object-oriented systems on top of PostScript by exploiting the dictionaries and the dictionary stacks. I leave it as an exercise to you, however, to think how you would use dictionaries to model not only methods, scopes for variables and methods, but also to implement inheritance. Think for a moment how a stack of dictionaries can be used to model inheritance of features between different classes, and you'll be on the right path. Thanks very much for listening. To sum up, I'll just let you briefly see the last 2 slides with the questions for further study.